Let's study the kinematics for a 1D motion with constant acceleration. So the starting condition here is for an object to have an acceleration ax equals a constant. So this condition is known. And then we start from here. Think about what's the property of, for example, velocity and also the displacement of this object as a function of time. And according to definition, ax is dvx dt. And since ax is known quantity, so let's think about how to solve from this differential equation, how to solve for vx. Okay, so let's move this, let's separate these variables, dt to the left side, and dvx is kept at right side. Then we get dvx equals ax dt. Now let's integrate this differential equation on both sides. And we start from t naught here for the initial time. And we integrate to a time instant t here. And correspondingly in the velocity integration, we have an initial velocity vx naught at instant t naught, and we want to integrate to some unknown velocity vx. Okay. And I also, in order to differentiate the integration variable and also this upper bound, let's change this integration variable to t prime, and this one to dvx prime. Okay, so the left side gives us vx minus vx naught as the integration result, and the right side, because ax here is constant, so we get constant multiply t minus t naught. Now let's solve for vx, and vx is given by vx naught plus ax t minus t naught. So that's the expression of the velocity as a function of time. Okay, so now let's start from here and think about how to represent the result in a diagram. So if I plot vx versus t, I will get this straight line. That's a straight line here, linear relation. So get a straight line here, right, as the velocity as a function of time. Okay, so now think about how to calculate the displacement starting from this equation here. And remember that Vx is defined as dx dt, or the derivative of x with respect to time. And let's plug in this expression that we just obtained. So we get Vx naught plus ax t minus t naught equals dx dt. Okay, so again, in order to solve this differential equation, let's separate these variables. Let's move dt to the other side of this dx. And what we have here is dx equals Vx naught plus ax t minus t naught dt, and then we integrate on both sides. Again, we start from an initial time t naught, we integrate to a time instant t, and correspondingly we have x naught, and we integrate to x. Again, to differentiate between this integration variable x and the upper bound x, we use dx prime here, and similarly we use dt prime. And here we also change it to t prime in the integration. All right, so let's see what is this integration result. Left side here we get x minus x naught. And right side here, let's look at these two terms separately. So the first one, Vx naught, is a constant. So we get Vx naught t minus t naught. And the second term here, we have a linear t prime term. So the integration of this linear term gives us a quadratic. And remember, we have factor 1/2 here because of this linear integration. So we raise the order to 2. So we get t minus t naught squared. Okay, so here I already substituted in the integration bound. So if I write down this carefully, I will get, so let's look at this step here. So this integration gives me 1/2 ax t prime minus t naught squared, and then t prime goes from t naught to t. And the upper bound here gives me 1/2 ax t minus t naught squared. And lower bound, if you substitute in t prime equals t naught, then you get 0 here, right? Minus 0. Okay, so let's see some note here for getting this term. Okay, so if I rearrange all these terms, I get x equals x naught, the initial position, plus the linear contribution Vx naught t minus t naught, plus the quadratic contribution due to the acceleration. So that's t minus t naught squared. Okay, so if I look at the Vx versus t diagram, I initially have this straight line linear relation with t. And if I look at the meaning of integration, we know that the integration here is given by the area under the curve, right? So we are looking at this area here under this v curve here, right? Vt curve here. And the area under such a curve is has two components. One is you can say this one is the right triangle, and the other part of the area is a rectangle. Okay, so rectangle here, one side of rectangle is t minus t naught. The other side of rectangle is Vx naught. That's the height. And that gives me the area here. That's the rectangle. And the other one here, this expression corresponds to the right triangle. So if I look at this right triangle here, this area, right? So the length, one side of the right triangle is t minus t naught here, and the height is the difference in this final velocity and this Vx naught minus Vx naught. And that is given by Vx minus Vx naught is given by Ax times t minus t naught. Okay, so the area, the right triangle area is 1/2 t minus t naught multiply the height here, which is Ax times t minus t naught, which is 1/2 Ax t minus t naught squared. So that's the right triangle.